Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at prime numbers. So you probably know by now, a number like 23 is prime. So we've been told it's prime because you can only write 23 as 23 times 1. You can't write 23 as the product of any other positive integers. So 23 has exactly two factors, 23 and 1. But see, this here is actually the definition of irreducible, not the definition of prime. So why would we have always used the definition of irreducible rather than the definition of prime? Well, there are two reasons for that. Firstly, it turns out in the integers and in certain other sets called integral domains, which we'll learn about later, it turns out that in those sets that are integral domains, any number that's irreducible is prime, any number that's prime is irreducible. So those two concepts are logically equivalent in sets that have certain characteristics. That's the first reason we've given you the definition of irreducible rather than prime. The second reason is the definition of prime, which is here, is actually quite complicated. This one is so much easier to understand. So the definition of prime is here. A number p is prime if p divides ab implies that p divides a or p divides b. So what does that mean? Well, this symbol divides basically means is a factor of. So if p is a factor of a composite number ab, then what that means is either p is a factor of the first number a or p is a factor of the second number b or both. That's what we mean by prime. So that's a bit complicated. So let's look at a couple of examples. So we have 20 divides 60. In other words, 20 is a factor of 60. 60 is a multiple of 20. So 60 can be written as 12 times 5. So the thing is, we can write this number, that's a multiple of 20, we can write it as the product of two numbers, neither of which is a factor of 20. 20 is not a factor of 12, it's not a factor of 5. Turns out for a number like 7, which is prime, we can't do this trick. So we know, for example, 7 divides 98. 7 is a factor of 98. So you can't write 98 in this way. You can't write 98 as the product of two numbers, neither of which is divisible by 7. If we were to go through the factors of 98, well, we have 98 is 98 times 1. We can write it as 49 times 2. It's not divisible by 3, 4, 5, or 6, but it is divisible by 7. So if I want to write 98 as the product of two positive integers, I can do it in three different ways. Notice that in each of them, they always include at least one of the number that is divisible by 7. I can't find two numbers that multiply to 98 where neither number is divisible by 7. So that's why 7's prime and 20 is not. As I said, this definition here is just the definition of irreducible, but when we're talking integers, all primes are irreducible or irreducibles are prime. All right, let's now look at the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic states that any whole number greater than 1 can be written uniquely as the product of primes. So we saw, for example, that 20 was not prime. So that means I can find some prime factors of it. So usually to find these prime factors, we do a factor tree. So we can do 20 is 10 times 2 and 10 is 5 times 2. So 20 is 5 times 2 squared. So you can't write the prime factorization of 20 in any other way except changing the order to 2 squared times 5, which is pretty much, well, it is exactly the same thing. So that's what we mean written uniquely. Product means times, so we've got some primes times together. On the other hand, of course, 7, which is prime, well, it's already prime. It's just itself. So you can do that with any number greater than 1. You can always decompose it into primes. Now, it's really important we note here that 1 is not a prime. 1 doesn't satisfy our idea of primes in that it doesn't have exactly 2 factors. And that's really important, because if 1 were to be a prime, then I couldn't write the factorization uniquely. 20 equals 5 times 2 squared, I could also write as 5 times 2 squared times 1. So here I've added in an extra number, but because 1 is not prime, this here in green is not a proper prime factorization. So this fundamental theorem of arithmetic is really important. It shows us how just as elements are the building blocks of chemistry and they're the building blocks of compounds, prime numbers are the building blocks of the integers. And in fact, the fundamental theorem of arithmetic can be used to prove that there are infinitely many primes, and we'll look at such a proof in the lesson. But now we're going to look at another proof that there are infinitely many primes. So here we're just going to call M1 equal to some number n. N may be composite or may be prime. We're just going to let n be some whole number greater than 1. So I'll use this notation, which means n is a member of the integers. So now we're going to look at M2. So M2 is our original number times the next consecutive number. So the idea here is that if I write M2, if I find any number that's the product of a number and the next number, then there must be at least 2 primes in this factorization. N and n plus 1 could be primes, in which case you'd have 2. If n and n plus 1 are composites, then there'll be more than 2 primes in the prime factorization of this. The important thing to note is that for any 2 consecutive numbers, they do not share any prime factors. It's impossible for them to do it. Like 14 and 15 will have different prime factors. So I can keep going with this. So what I've done is I've taken M3. This part of it is M2. So M3 is M2 times M2 plus 1. Again, I'm multiplying a number M2 by the next consecutive number. Again, this M2 and this next consecutive number will not have any primes in common. So I'm introducing more primes into the prime factorization of M3. There were at least 2 primes in M2, and then we're adding in this number. Either it is going to be prime or it's going to have additional prime factors than we had in M2, because M2 and the next consecutive number share no prime factors. So the idea behind this proof is we can keep going infinitely long. We can keep doing this. We can take the previous, so Mn, we'll take the previous value of n, and then we're going to multiply it by the next consecutive number. So if we do that, each time we do this, we are going to introduce at least 1 new prime factor, because these 2 do not share any prime factors. Consecutive numbers never do. So we can keep going infinitely many steps, and at each step we're introducing a new prime, so there must be infinitely many primes. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.